Okay guys, today we're going to start looking at lengths of curves in a plane. So if we had a curve like this, we're not finding the direct length here, we're actually finding this length along the whole curve. Okay, we've got a formula here which is the length is from the starting point, so that would be A, to our end point, that would be B. The derivative is the integral is 1 plus dy dx squared. Or A to B square root 1 plus f dash of x squared dx. We could test it, I guess, like to make sure that it works. If I had y equals x. Alright, so just so we said, we wanted to go from 0 to 4. If we were to sketch y equals x, there's 0 to 4. We would know that that length, that'd be 4, that'd be 4. So we would get 16 plus 16, root 32, which would be 4 root 2. So we should get 4 root 2 when we integrate. So let's now try that from 0 to 4. Of what's our formula? So we know f of x is x, f dash x is 1, so it'd have 1 plus 1 squared dx, which we know is 0 to 4 root 2 dx, which would be root 2x between 4 and 0. So when we sub 4 in, we get 4 root 2. When we sub 0 in, we get 0, so we get 4 root 2, which is exactly what we got doing it as a straight line. Now, let's have a look at a curve. So find the length of the curve, y equals x to the 3 on 2. Now, if you didn't know what it looks like, it's basically, because my top power is higher than my bottom power, it's going to curve upwards like a parabola. Wouldn't be quite as steep as a parabola, between 1 and 4. So there's my curve there. Now, if we wanted to, we could find the direct length and just make sure that this length is longer. You'd know that it has to be longer. It can't be the same length because it's got to be greater than the direct length. To integrate, or to find the length, dy dx, we've got to find that first. So 3 on 2, x to the half. Length is our integral between 1 and 4. Square root 1 plus f dash of x, or dy dx, squared dx, which we know is 1, 4, square root 1 plus, if we square this, we're going to end up with 9 on 4. X to the half squared is just x, so 9 on 4x dx. Okay, what are we going to do here to integrate this thing? We have the integral of, we could take out 4 as a common factor, so 1 to 4 square root, if I took out a 4 as a common factor, I would end up with a half when I take it outside, and this would end up being, if I put a 4 on the bottom, I get a 4 on the top. So we take out a quarter, which is a half, and of course we could put that right out the front. So we could say a half square root 4 plus 9x dx. Okay, how do we integrate something like this? We've got a rule. 1 to 4 with a half, 4x. 4 plus 9x to the power of a half dx. Okay, our integral we know is 1/2. It's 1 on our new power, which is a half, 3 on 2, times the coefficient of x, which is 9, and then times 4 plus 9x to the 3 on 2, between 4 and 0. Okay, out the front, we're going to have 3 on 2 times 9, which is 27 on 2. So I'd get 2 on 27. But we know we've got a half out the front as well. So if this was going to be 2 on 27 and I multiply it by half, I get, let's put it out the front, 1 on 27 because it's constant. And then we're going to have 4 plus 9x square rooted and cubed, because to the power of 3. Okay. Now, when we put in 4 and 0, what are we going to have? We're going to have 1 on 27. When we put 0 into that, it's not going to equal 0 because it's got a square root. Okay, so we've got, put 4 in. I get 4 plus 36, which is 40. 4 plus 36, which is 40. 9 4s are 36, yep. Cubed and then square rooted. So what's the square root of 40? It is 4 root 10. 2 root 10. What am I talking about? So because it's the square root of 40, it's 2 root 10, and then we've got to cube that. Minus, if we put 0 into that, we're going to, oh, it's not 0, it's 1. Okay, so we put 1 into that. Paste to make sure you copy the correct thing across. Okay, so if I put 1 into that, I'm going to get 4 plus 9, which is 13, square rooted and cubed. So root 13 cubed. Okay, so this is a little bit nasty, but if we square, so we've got 1 on 27. If we cube 2, we get 8. If we square 10, if we cube root 10, we're going to get 10 root 10. That makes sense. And then we also have to cube root 13, which is going to be 13 root 13. That makes sense. Okay, so our answer is 80 root 10 on 27 minus 13 root 13 on 27. That is our length from, not from there, from 1 to 4. Now we quickly did Pythagoras. 64 square root 8. So this would be 1, 1, and this would be 4, 8. And 1, 1. If we found the direct line distance, we're going to get 49, 7 squared, plus 3 squared, 9, square rooted, which is square root of 58, which we know, what's a square root of 58? It's going to be a bit less than 8, so let's say 7.6. And then if we checked out this other value, okay, so let's go. Actually, we can use arc length. In here, you've got calculation, line, arc length. Our expression was x to the power of 3 divided by 2. Start was 1, finish was 4. So that's our exact length. And if we want a decimal, we get 7.63. And if we worked out our direct line, that was root 58. So you can see it's longer, but not much. It's almost a straight line. Because if you sketch x to the 3 on 2, Let's go back and have a look. If we sketch y equals x squared, and if you sketch x to the power of 3 divided by 2, you'll see, and if you sketch x, you can see that that line isn't that far off being straight. I mean, it's not straight, but it's not that far off it. Okay, so that's our arc length, and that's using just standard Cartesian equations. If we have a parametric curve, so I've got our x components in terms of f of t and our y components in terms of g of t. If we know the values of t and we know what x and y are, we use, it's pretty much the same formula, but it's the change in x over the change in t squared. So it's basically just Pythagoras' theorem. The change in your x values over the change plus the change in your y value, and then the square root of that, and then adding up. So if like we had a curve, we'd be adding up these little chunks of lines infinitely, and then that makes up what the length of the whole thing is. Because the change in x is this value, your change in y is this value. If I find that length there, which is what the square root of the change in x squared plus the change in y squared, so that's the change in y squared, change in x squared, and then square rooted, I'm getting this length here, but I'm doing it infinitely many times, so I'm adding up every single little bit of line together, and that gives me my length. Okay, so length of the curve defined by the parametric equations, cos of t and sine of t for 0 is less than t, which is less than 2 pi. So we start with x equals cos of t, so dx dt is negative sine of t. Y equals sine of t, so dy dt is equal to cos of t. Okay, then we use our formula. Length is from 0 to 2 pi, the square root of dx dt squared, so negative sine t squared, plus cos t squared dt. Now you can see here this is going to end up being something nice. We know that this here underneath, because when I square root negative sine t squared, it's going to be sine squared t plus cos squared t, which is just 1, and the square root of 1 is 1. So we end up with the integral from 0 to 2 pi of 1 dt, which gives us t, 0 and 2 pi. So our length is 2 pi. 2 pi minus 0, which is 2 pi. Now this makes sense because if x is cos of t and y is sine of t, it's going to create a circle with a radius of 1, because our coefficients are 1. And if we want the length around the outside, it's just 2 pi, because we know our circumference is 2 pi r, and our radius is 1. So it should be 2 pi. We haven't stuffed anything up, which we haven't. There you go. Does it do it parametrically on the CAS? I don't think it does. Interactive calculation, line, arc length, expression. No, so that's only in terms of one variable. I don't know if you could do it in here, graph and table. We'll just check all of our... Okay, so let's put in our parametric equations. Cos of t, sine of t, we want it between 0 to 2 pi, and let's sketch it. So there it is, analysis, G-solve, distance. I don't know what distance is. Oh, that's finding the distance between 2 points. Analysis, G-solve, x, y, integral. Nope. Sketch. No, I don't think it does it. Yeah. Okay, so there's no way that you can work out the arc length of parametric equations unless you know how to do it by the formula. Of course, you can do it by the formula, so yeah, that's not too hard. Okay, so good luck with that chapter. Just remember, whether it's Cartesian or whether it's parametric, that's the only difference in the formulas. So, where are we? Yeah, try and finish off that last exercise, 8E, and soon we'll start on chapter 9. We're getting there.